Today, we are mastering logarithms and indices, a fundamental component of the Cambridge International A-Level Pure Mathematics 1 syllabus. You will learn to convert between index and logarithmic forms, manipulate expressions using the laws of logarithms, and solve exponential equations. This topic is a staple in the 9709 examinations, often appearing in questions involving geometric progressions, coordinate geometry, or as standalone algebra problems. Mastering this ensures you can handle any equation where the variable is trapped in the power. We begin with the core relationship between indices and logarithms. A logarithm is simply the inverse operation of exponentiation. The statement y equals a to the power of x is equivalent to x equals log base a of y. Here, a is the base, which must be positive and not equal to 1. X is the index, exponent, or power. And y is the argument, which must be greater than 0. When we write y equals a to the power of x, we are asking for the result of raising a base to a power. In the logarithmic form, x equals log base a of y, we are asking for the power to which the base must be raised to produce that result. Think of it this way: the base in the index form remains the base in the log form. The answer and the power simply swap places. Let's apply this conversion immediately to build fluency. Take the base, which is 5. In the log form, it stays as the base. The power, 3, becomes the result. So, log base 5 of 125 equals 3. This literally means 5 raised to the power of 3 gives 125. Here, the base is 2. The result of the log, 4, is the exponent. Thus, 2 to the power of 4 equals 16. Mastering this mental loop is the quickest way to solve simple log equations in an exam without reaching for your calculator. Concept: graphs of f of x equals a to the power of x, and g of x equals log base a of x. Because logarithmic and exponential functions are inverses, their graphs are reflections of each other in the line y equals x. Let us look at the exponential function first. For a base a greater than 1, it always passes through the point 0, 1, because any base to the power of 0 is 1. It has a horizontal asymptote at y equals 0, meaning it never touches the x-axis. The domain is all real values of x, but the range is y greater than 0. Now, for the logarithmic function, the coordinates swap. It passes through 1, 0. It has a vertical asymptote at x equals 0, which means the argument of a logarithm must always be positive. The domain is x greater than 0, while the range covers all real values of y. In your exam, if you are asked to sketch these, ensure you clearly mark these intercepts and asymptotes. To manipulate more complex expressions, we use the 3 fundamental laws of logarithms. These laws are essential for simplifying equations before solving them. The multiplication law tells us that the log of a product is the sum of the logs. This mirrors the index law, where we add powers when multiplying terms with the same base. The division law states that the log of a quotient is the difference of the logs. Again, this is the inverse of subtracting exponents during division. The power law is perhaps the most useful for exams. It allows us to move an exponent down to become a multiplier. This is the key that unlocks the variable when it is stuck in a power. Finally, remember these two identities. Log base a of a is 1 because a to the power of 1 is a. Log base a of 1 is 0 because any base to the power of 0 is 1. Let's use these laws to simplify a typical exam-style expression. Express 2 log base a of 3 plus log base a of 4 minus log base a of 6 as a single logarithm. First, we address the coefficient in front of the first term using the power law. 3 squared is 9, so we have log base a of 9 plus log base a of 4 minus log base a of 6. Next, we apply the multiplication law to the first 2 terms. This gives us log base a of 36 minus log base a of 6. Finally, we apply the division law to combine the remaining terms. which simplifies perfectly to log base a of 6. By following these steps, we have condensed a complex expression into a single clean term. In the exam, always look to clear coefficients with the power law first. Solve 3 to the power of x plus 1 equals 20, giving your answer to 3 significant figures. When the unknown variable is in the exponent and we cannot easily rewrite both sides with the same base, we take the logarithm of both sides. We usually use the common log, base 10, or the natural log. Log of 3 to the power of x plus 1 equals log of 20. Now, we apply the power law to bring the exponent down. Note that the entire exponent, x plus 1, must be treated as a single quantity in brackets. X plus 1 times log of 3 equals log of 20. To isolate x, we first divide both sides by log of 3. Then, subtract 1 from both sides. Using a calculator, log 20 divided by log 3 is approximately 2.7268. X is approximately 1.73. The final step is rounding to the required degree of accuracy. The question asks for 3 significant figures. Always check the rounding instructions in the question. 9,709 papers are very strict about this. Let's look at a typical Cambridge 9709 style question. Solve the equation 5 to the power of 2x minus 1 equals 7 to the power of x, giving your answer correct to 3 decimal places. Because we have different bases, 5 and 7, and the variable x on both sides, we must take logarithms of both sides to release the exponents. Step 1. Log of 5 to the power of 2x minus 1 equals log of 7 to the power of x. Apply the power law to both sides. Notice how the brackets are essential for the term 2x minus 1. Now, we need to isolate x. We expand the brackets on the left-hand side. Rearrange the equation to bring all terms containing x to one side and constants to the other. Factorize x out of the left-hand side. Finally, divide by the term in the brackets to get the exact expression for x. Using a calculator, compute the values carefully. 2 log 5 minus log 7 is approximately 0.553. Dividing log 5 by this gives x equals 1.262, rounded to 3 decimal places. Alternative methods, like trying to use a change of base formula immediately, are often more prone to algebraic errors. Expanding and factorizing is the most robust way to secure all marks in the exam. In Cambridge examinations, students frequently lose marks due to avoidable errors. Let's look at 3 critical ones. The first mistake involves incorrectly applying the multiplication law. A very common error is thinking that the log of a sum can be split. It cannot. The log laws only apply to products, quotients, and powers. Mistake number 2 is missing brackets when using the power law. When you bring an exponent down, if it contains more than one term, you must use brackets. Without them, you will likely only multiply the first part of your expression by the log, leading to the wrong result. Finally, mistake 3. Invalid arguments. Remember the graph we studied. The domain of a logarithm is x greater than 0. If you are solving a quadratic equation in terms of logs and get a negative value for the argument, you must reject that solution as it is undefined. Visually, the graph never crosses to the left of the y-axis, confirming that the argument must be strictly positive. To achieve top marks in Pure Mathematics 1, you must understand how examiners award marks for logarithms. Method marks are awarded for taking logs of both sides and correctly applying the power law. Even if you make a calculation error later, showing the step where you bring the exponent down will often secure your first 2 marks. Accuracy marks. Ensure you follow the rounding instructions precisely. If the paper asks for 3 significant figures and you provide 2, or you round incorrectly to 3 decimal places instead, you will lose the final accuracy mark. Show all steps. Do not go directly from the question to the answer using a solver. Examiners need to see the algebraic manipulation. Write down the division of the logs before you put them into your calculator. This provides a safety net. If you mistype a number in your calculator, your written work proves you knew the correct method. Base consistency. Keep your logs in the same base throughout a calculation. Whether you use log base 10 or natural log, stick to 1. Mixing them in the same equation is a recipe for disaster. It is time to test your understanding. Please pause the video and attempt these 3 questions before we go through the solutions. Easy. Write 3 to the power of 4 equals 81 in logarithmic form. Medium. Solve 5 to the power of x equals 40. Give your answer to 3 significant figures. Hard. Solve the equation log base 2 of x plus log base 2 of x minus 2 equals 3. Take your time with the algebraic manipulation, especially on the hard question. Once you are finished, resume the video to check your work. Let us go through the solutions to see how you performed. For the easy question, we have 3 to the power of 4 equals 81. Using the relationship we learned, the base 3 remains the base. The power 4 becomes the result of the log. For the medium solution, we solve 5 to the power of x equals 40. Take logs of both sides. Log of 5 to the power of x equals log 40. Use the power law. X log 5 equals log 40. Divide. X equals log 40 divided by log 5. Using a calculator, x is approximately 2.292, which rounds to 2.29 to 3 significant figures. Now for the hard solution. Log base 2 of x plus log base 2 of x minus 2 equals 3. First, combine the logs using the multiplication law. Log base 2 of x times x minus 2 equals 3. Now, convert the logarithmic form back into index form. The base is 2 and the power is 3. Expanding the left side gives x squared minus 2x equals 8. Rearrange into a quadratic. X squared minus 2x minus 8 equals 0. Factorizing gives x minus 4 times x plus 2 equals 0. So x equals 4 or x equals negative 2. Crucially, we must check the original arguments. We cannot take the log of a negative number, so we reject x equals negative 2. Final answer, x equals 4. To summarize our lesson on logarithms and indices. Logarithms and indices are inverse operations. The statement y equals a to the power of x is fundamentally the same as x equals log base a of y. Understanding this loop allows you to switch forms to solve equations. Master the 3 laws of logarithms. The multiplication, division, and power laws are your primary tools for simplifying complex expressions and moving variables out of exponents. Asymptotes and intercepts. Remember that the graph of a log function has a vertical asymptote at x equals 0 and passes through 1, 0, while the exponential function has a horizontal asymptote at y equals 0 and passes through 0, 1. Always check for valid solutions. When solving logarithmic equations, ensure that your final answers do not result in a negative argument, as logs of negative numbers are undefined in the real number system. Precision is key. In the 9709 exam, follow rounding instructions to the letter, usually 3 significant figures for non-exact answers, to ensure you don't lose marks on the final step.